So we'll start with a series of 5 presentations from people in our faculty this time, doing various things with AI, from the more sophisticated to the more end-user uses of AI. And we will also finish with a talk that will give us various resources where we can learn and find out how to start if we haven't done it before. But it will be a little more than just how to start, so stay all the way to the end. And we'll start with Liam Bernheimer from the School of Chemistry.
Thank you, Ron. Hello, everybody. So I'm a PhD student at the School of Chemistry at Guy Cohen's group. And before you delve into the next few presentations that show you tools that you might use yourself, here I will show you how we use the machine learning and AI in actual physics and science. So to begin with a short introduction, to describe systems in reality, usually classical mechanics describe them quite well. And if I want to know everything I want about a state, all I have to know is the current positions and the momentas of particles in the system. And you can see, for example, a solar system or this cartoonish description of an atom. If we know the status of the particles at one time, we can easily know what will happen in the future. But as you probably know, for small systems such as atoms, this is not working quite well. And we need quantum mechanics to describe any state. So essentially, we would have a wave function which describes the probabilities of the particles being at certain positions at any time. And you would have this sort of complex function that you have to know everything about to know this state. To show a simple example for this, if you think about a small, simple system of particles in a chain, a spin chain, you would have, each particle could have one of 2 states, up or down, or 0 or 1. So in classical mechanics, all I would need to know about this system to describe it is just the state of each of the particles. And the number of data points I would need to know is only the state of each particle, meaning the information grows linearly with the number of particles. But in quantum mechanics, since I need to know the probability of being in each possible state, and I would need to know the coefficients and the probabilities for each of those states, so the question is, how many states are there? So if you look at the simple case of one particle, in classical mechanics, the system would only be described by the state of the system. So in this case, 0. But in quantum mechanics, you have 2 possible states, and you need to know the coefficients and the probability of being in any one of them. If you have 2 particles, then you can already see that the large difference. Here you have 2 values that you need to store, and here you have 4 values for each of the 4 possibilities. If you have 3 particles, then it's already not, it's big enough, too big for the presentation. You have 8 options and only 3 in the classical scenario. So essentially, I hope you're quite a little convinced that quantum mechanics is a big data problem, as you have a lot of information that you need to treat, and it's quite hard to treat an exponentially large amount of data. Now, from YouTube videos, and probably you played with DALI and tools like that, you know that somehow machine learning is able to describe very complex functions and states. For example, if you have an algorithm that can generate a picture of a cat, in this example, you have a picture of 256 pixels in each direction. Each of the pixels can have 1 out of 16 million colors. So the number of possible pictures is 16 million to the power of 60,000, which is quite a huge number. Yet still, the machine learning algorithms are possible to describe and generate a cat somehow. They are able to learn something in this space. So this kind of logic also works in wave functions and quantum mechanics. If I have samples of data and samples of a wave function and probabilities, I would be able to learn the curve and the description in the entirety of space. This also generates for higher dimension. So this is a small example of it. This plot, by the way, I made entirely with ChatGPT. I just gave it the prompt and the code worked out of the box. So that's nice. OK, so given that, I will introduce a bit of more what we do with it. In quantum chemistry, something of interest to us is the ground state wave functions of systems. This is essentially the state of the system which has the lowest amount of energy. And this is of interest because usually in room temperature, and also we sometimes care about lower temperatures, the molecules and systems that we talk about usually are in this lowest energy ground state wave function. So it is of interest to us to find it somehow. There is a method that we can develop using something called Feynman's path integral formulation, which enables us to start from any initial guess of a wave function, described here by this sort of Gaussian. And we can apply this tool onto this initial wave function to get a wave function that is closer to the lower energy state that we're after. So to do it, we can do it only for a small amount of points in space, since the entirety of space is infinite, so we must do it for small sampled points. So if we only ask about one point, we first choose the position that we want to know the value of the wave function at that in a state which has lower energy. Then we sum upon these paths that essentially are the actions of these paths, which is determined in physics. And if we repeat this procedure for many points, we can get a sort of a sample of the wave function in many points in space. Using machine learning, essentially, we can pass a line through these points. And with the hope, and it does work in practice, if this is useful in many dimensions, we can describe highly dimensional functions and wave functions with only a few sample points which we generate in this manner. So essentially, if you repeat this procedure many times, because you can only do it for short differences of energy, essentially, you can start with any ragged wave function which has non-physical shapes, and very quickly you could see that we go to the ground state wave function. In this case, it should be a nice Gaussian for the harmonic oscillator. So this is a nice tool. And now I will show you how we can do even something a little cooler, which is more practical in physics. So in atoms, and the wave functions that we care about are atoms of particles that are called fermions. They exhibit this particular phenomena where if you switch the position between them, the wave function will change its sign. Usually in most numerical methods, this is enforced by describing the wave function as a determinant of other functions. And you can quite easily, I hope, be convinced that if I switch the position of x1 and x2, or replacing the rows, the sign of the determinant will change. This calculation of the determinant has a numerical complexity of n cubed, meaning if I have many electrons, as most molecules have, it would be quite expensive to perform this operation. Now, within this framework of using machine learning that I showed you, we have developed this new technique to enforce this anti-symmetry upon wave functions. Essentially what we do is, instead of storing the entirety of the wave function, like with the determinant, we only store, in this two-particle case, one half. So you see only this colored bar, this colored area is known to us. And this is the area where x1 is smaller than x2. Now, if I want to know what is the value of the wave function at this area, which is outside of this colored plot, all I would have to do is simply sort the particles and their positions, essentially exchanging the order. Instead of 2 and 1, I would have 1 and 2, and give each other the other's value, and just apply a negative sign to the value of the wave function that we already have, right? So I apply this sorting operation upon the position of the articles and apply the sign of this permutation. And this way I can only store this factorial part of space instead of the entirety of it. Now, the sorting operation has a complexity of n log n if I use a quicksort algorithm, which is much better than the n cube that I showed you earlier and the n squared that maybe state-of-the-art methods can achieve. Now, this was not possible without the machine learning, since this area here, the node, can be non-continuous sometimes within this procedure, which is a problem for many methods, since the kinetic energy, which is calculated by taking the derivatives of this wave function, is necessary. But as I showed you before, we didn't use any derivatives at any point. We only summed upon paths. So this combination of these tools together allowed this nice technique to be viable. Now to finish, I will show you some nice pictures that we have generated using this method. Essentially what you see here is the electron density, which is somewhat like the wave function, but the probability of an electron being at some of the colored points is higher. And here you have a 6-electron system where we increased the interaction between them and found nice crystallization as the interaction strength grew. This is called Richner crystallization. It happens when electrons are bunched together, essentially. And seeing this nice picture would not have been possible without enforcing these symmetries thanks to this method that I showed you earlier, which is also possible for other symmetries, not only the anti-symmetry of the electrons. So this is essentially it. I hope it was approachable.
Thank you very much. Any questions? So how extendable is this? I mean, sounds like a starting point for doing much more.
So essentially we got up until 10 particles in 2 dimensions, which is quite a large number of dimensions already. But the next point would be, of course, to use the actual real atoms, where the special potential of the atoms, which is a little problematic, is the next thing to try and use. But it is quite general. I mean, applying any potential is quite easy in this method, and only seeing if it works is the only question.
And how long does the calculation take?
Something like this would take about maybe a few hours up to a night, but the implementation is rather simple and not really professional. So probably it could be much faster.
Thank you very much.
Thank you.
Yeah, microphone.